Back to another video on Daishinfinity. Today's topic is going to be the normal distribution and the derivation of the normal distribution. Since the normal distribution is called a bell curve, I'm going to explain to you some very important aspects and very important facts about this bell curve. Now, first of all, if we look at the bell curve, we have a lot of things to say about it. We have the mean. The mean is in the middle of the in relation to the bell curve, since it has the biggest value of the function. The biggest value of the function, to find it, we have to take the derivative and make it 0, if you know what it means. And we also have the standard deviation sigma notation, which is the small sigma letter written on the top of the bell curve. And since I wrote some tangent lines over there, I'm going to tell you something in a few minutes. And I also wrote the general formula of the normal distribution, which we will derive from ourselves by using differential equations, substitutions, also like some, we are going to use some theorems too. Yes. So to introduce some of the mean and the variance and also the standard deviation, I'm going to talk about the mean. The mean is very simple. We have to calculate the mean by multiplying the amount of trials and errors we had and multiplied by the probability of the outcome. Now, the sigma notation is also called the standard deviation, which is just the square root of the variance. The variance is also calculated by the infinite sum, no, not the infinite sum, the finite sum from I going from 1 to n of the bracket xi minus mu in square times pi. So for every xi and pi, we have all the numbers over here. I wrote x1, x2 over here. And we also have the pi plus 1, so we have the p1, p2, and so on. To calculate it, we have to calculate the standard deviation by taking the variance and the square root, which would be x1 minus mu squared times p1 plus x2 minus mu squared times p2, and so on and so forth. Now, if we look at the bell curve, I also wrote something which is called the distance between the mean and the xi's. The distance between the xi's and the mean is also called the distance function, d of x, which we can write as x minus mu. So yeah, I'm going to tell you that afterwards, but we have to analyze and think about the rate of change and how the rate of change changes over certain distances. So we can see, if we look at xi away from mu, from the mean, we can see when the data are normally distributed that the rate at which the frequencies fall off is proportional to the distance of the source of the mean and to the frequencies themselves. So I'll write that again. So since I wrote this, it means that for every distance we go, the rate will proportionally change, and the rate at which it changes is a number, since it is proportional to the distance of the source of the mean and the frequencies themselves. So we can write the rate of change, which is just the rate of x of y, which means if it's just a derivative. And the derivative actually corresponds to saying that we have a function, or let's say f, and it's negative, or a constant which is negative. And let's call f just k, so I'm just ignoring f. F was a wrong substitution. I'm just going to say the rate of change is minus k, okay? So now we have something very important, and k can be any real number, so we will write that k is element of the real numbers. Now, since we also have the distance d of x is x minus mu. Now let's see, if x is here and mu is here, the distance between x and mu is going to be this, and this is going to be x minus mu. But imagine x is over here, smaller than mu. So for all x smaller than mu, x minus mu is going to be smaller than 0, since it's going to be negative, and we don't want negative numbers. So the way to do this, we're going to take the absolute value. So we're not going to put the brackets on. We're going to put the absolute value on both sides, so x minus mu, since we all want the same distance if we go left and if we go right. But for the derivation, we're going to only concentrate on the right side of the bell curve, so I'm just going to concentrate on this side of the bell curve, because the bell curve is symmetrical, and we can just always multiply it by 2 so that we get the whole bell curve. Now, since we have all the information, we can rewrite the differential equation that the rate of change is a constant times the distance between them. I'm sorry, I forgot the absolute value, x minus mu, times the original function. In order to solve this differential equation, dE, I'm going to divide both sides by y, so that we get y prime divided by y is equal to negative k times the absolute value of x minus mu. Now if we see this, we have a function's derivative divided by the normal function, and we have one fact, that the integral of the derivative in the numerator and the denominator is going to be the ln function of the original f of x plus c. So we can rewrite and put the integral signs over here, put the dx over here and the dx over here. And since minus k is a constant, we can put it outside. So we in orderly say that we have ln y of x plus c1, because we also going to get c2 is going to be negative k times the integral of x minus mu dx. Since x minus mu is another function of itself, we're going to do another substitution, that x minus mu is going to be some kind of eta. Now eta can be u or a or anything. Now I'm going to differentiate both sides. The eta is going to be dx. Now since we have dx d eta, we can rewrite it as the negative k times eta d eta, which is going to be 1/2 eta square plus another constant c2. Since we have c1, c2, I'm going to bring the c1 on the other side, and we get another capital C. Let me call it capital C, or like c3, I'm going to call it c0. So ln of y is going to be negative k over 2 eta square plus c0. Now we're going to take the e on both sides, because e to the ln of y is going to be the ln of y, is going to be the y, I'm sorry. So we're going to have y is equal to e negative k square, k over 2 eta square plus c0. Now eta square is x minus mu square, and c0 throughout the exponential rules, we can do it and separate them into two exponents, and we have e to the c0, which is another constant. So I'm going to tell you it's just a capital C times e to the negative k over 2 times x minus mu squared. Now we have a very nice crazy looking function, but we also have the k and the c to find it. So I'm going to find the c, for instance, and the very funny thing is this: the integral from minus infinity to plus infinity for any real number for a function which has something to do with probabilities is always going to be equal to 1, since all the probabilities added together should equal to 1. If it's more, then it doesn't make sense for our universe. So we can rewrite the integral from minus infinity to plus infinity, I'm going to call this next time on the real numbers, of c times e to the negative k over 2 times x minus mu squared dx is going to equal 1. Now this looks very, very scary. Since this looks very scary, I'm going to make a new substitution. I'm going to let k over 2 x minus mu square going to equal it u square. Why did I call it u square and not u? If I call it u and take the square root on both sides to get the x out, I'm going to have a problem with the square root of u, and I don't want the square root of u's. So I'm going to do it the u square, so that if I take the square root on both sides, I get normal u. So if I take the square root on both sides, I get the square root of k divided by 2 times x minus mu is equal to u. Now I can differentiate them both sides. I'm going to differentiate this equation because it's easier to do instead of doing the other one. It's going to do it's going to equal the same thing. It's 2u du is just k over 2 times 2 times x minus mu times 1, because of the derivative and the rule of, you know, the smaller functions. So we have k x minus mu dx. It's not that hard. And now we're going to get u, for instance. Since u was this thing, I'm going to tell you what u is. U was this one. We can substitute this in to this equation, and we get du is equal to you know, the quotient of those two, which is going to be pretty complicated, but we can cancel things out. So we get k times x minus mu dx divided by the square root of k over 2 times 2 times x minus mu. I hope I got everything right. Now I can cancel x minus mu's out, and then I'm going to talk about the k's and the 2's, since they are a little complicated. Now I'm going to scroll down and write du is equal to, I'm going to split it up in k divided by the square root of k, and I'm going to put the square root of 2 on top because it's on the bottom, divided by 2 dx. Now square root of 2 divided by 2 is the same thing as 1 over the square root of 2. K divided by the square root of k is going to be k to the 1 minus 1/2 through the potential exponential rules. We get square root of k over square root of 2, which is going to equal to the square root of k over 2 dx. Since we want to solve for dx, we have to multiply square root of 2 divided by square root of k, so we get square root of 2 over k du is dx. Now we get all the information, and we're going to plug all the information into our equation, which is going to be crazy, but I think we have no problem. So it's going to be the integral of the real numbers of c, and c I'm going to put it outside, times the integral of the real numbers, I already said it, e to the negative u squared du. And I'm going to put the square root of 2 over k over here. It's going to be a little messy. I'm going to write it again here. So it's going to be c square root of 2 over k, and then the infinite integral, which is going to be equal to 1. Now this integral is a special integral, and we cannot really solve this integral without using some special tricks. So the special trick, we have to be very smart and square both sides. Now we square both sides because we want to use a theorem called Fubini's theorem. I'm going to write this down. Fubini's theorem. Fubini's theorem states that if you have a function or an integral I, and you multiply or like intersect it with the same integral I, which is going to be I square, it's going to be equal, for this example, the real numbers, and then I can say that this is going to be negative x squared plus y squared dx dy. So it's going to be an interchange of x and y's. So I'm going to integrate x and then I can integrate y, or I can do it the other way. I can integrate y and then x. It's going to not change anything because it's an intersection of these two. It's pretty abstract to explain, so I will try to explain it in another video, but it will take a long time. So I'm going to think about it. Since we have this theory, when we square both sides, we will have 2 over k times c squared, and the c squared I'm going to put it on the numerator, and the integral squared is going to be equal to the integral of the real numbers times the integral of the real numbers of e to the negative x squared plus y squared dx dy is equal to 1. Since we have dx dy is equal to 1, we can do another substitution. If you see x squared plus y squared, now I'm going to tell you what x squared plus y squared is going to be in a trigonometric way. So x squared plus y squared can be understood as the function of x comma y of this thing, and this will demonstrate the normal circle. Now if we have the normal circle, the radius is always constant, which we can write here, which is the hypotenuse of this right triangle. Now this right triangle consists of the y coordinates and the x coordinates. The y coordinates is over here on the right hand side, and the left and the down side is going to be the x coordinate. Now if you put in let's say theta is a degree, then we would write the left hand side, or let's say the x component, as r times cosine of theta, and over here we can write it as r times sine of theta. How you get this, I'm going to explain it to another video. Just wait until the video comes out. Since we have this, we can say that r cosine theta is equal to the x component, and r sine theta is the y component. If we're going to square both sides, since we want to go to x squared plus y squared, we get r squared cosine squared theta and r squared sine squared theta. Now if we add these up, it's going to be x squared plus y squared, and I'm going to take the r squared out of the bracket. I'm going to say r squared times cosine squared theta plus sine squared theta. Since cosine squared theta plus sine squared theta is equal to 1, r squared times 1 apple and 1 apple are the same, we can say it's r squared. Since we have this, we can put the r squared into this thing. So we would have something like this: 2c squared over k times the integral e to the negative r squared. Now we have to put some dr's in it. And to do this, I'm going to explain to you how we can get to this point. Now, as I already drew something, this is a small set of small dy's, dx, and the dA. The dA is the difference in area. Now, we have the circle right now, and we have a surface, and we want to calculate the difference of the surface areas. Now, the x component and y component are going to make up a a rectangle. We can say the difference of the area is going to be the multipliers of x and the y's. But we can also say that the sides of the difference of the area, if we look at the area, which is this one, what I'm talking about, this side and this side, respect to this one, which is the radius here, it's going to have a really small d theta, which means this small length is going to be d theta times r, which is the same thing as the arc length. And since we have a square or like a rectangle, we have to multiply by dr, which is the next side. So we are going to multiply r dr d theta, or theta. Since we did this, we can put this in our equation, and say that we have r dr d theta is equal to 1. Since we have the r inside now, we can make another substitution. And the substitution is going to be as follows. I'm going to let omega equal to r squared. D omega is going to be 2r dr, such that d omega divided by 2 is going to be r dr. Since r dr is d omega divided by 2, the divided by 2, I'm going to put it outside the integral. It's going to lead us to 2c squared over k. The integral from 0 to 2 pi, the integral from 0 to infinity of e to the negative omega d theta equaling 1. Now the reason why I put the lower and the upper boundaries is going to be as follows. I had dr times r. The r dr is respect to the radius. The radius of convergence of this bell curve is infinite, since the bell curve can go to infinity. This is why we have to calculate the surface of the all the radiuses from 0 to infinity. Then we have the first bell curve, and we have to calculate the the bell curves in the whole full cycle, because we have 3 coordinates now. We have the x, the y, and the z. The z is going to be f of x comma y. And I just wanted to tell you that the curve looks like this on the x side, and the curve looks like this on the y side. So if you want all the curves, you would have to take the integral of all these things. And to go a full cycle, I'm going to make it thick. To go a full cycle, we need 2 pi radians. This is why we're doing the 2 pi. Now, since we have the knowledge to calculate this integral, it's going to be just the negative of the function. We can put the limit for the infinity, but I'm just going to ignore it because it's not that important for this video. E to the negative e to the negative omega from 0 to infinity times d theta is equal to 1. Since all e functions with a negative exponent go to 0, this is going to go to 0. If we put in 0 into omega, we have e to the negative 0, which is 1, but we have the minus 1. And because of the f of a, capital F of a minus capital F of b, we would have negative 1, which is going to equal to 1. So this whole chunk is going to equal to 1. Now, this will lead us in being 2c squared over k, 0 to 2 pi of 1 d theta. 1 d theta is theta from 0 to 2 pi is going to be 2 pi minus 0, which is 2 pi. So we have an answer of 2c squared k times 2 pi 1. Okay. Now 2 times 2 is 4. Elementary stuff. We have 4c squared over k. Or I think I made a mistake. I've made a mistake that the 1/2 will cancel out with the 2. So the 2 is already cancelled out here, since we have the 1/2. We had the 1/2 at the top and the very bottom. So we had the 1/2 here, over here, and the 1/2 will cancel out with the 2 here. So we don't have the 2 here, and now we have the 2. So I'm sorry for this mistake. It's going to be 2c squared. So c squared over k, c squared over k times 2 pi is equal to 1. Now if we calculate for c squared, it's going to be that c is equal to the square root of k over 2 pi. Very nice. This would lead us in the following function: y is equal to k over 2 pi times e to the negative k over 2 times x minus mu squared. Now we have found the c, but we still have the k, and we want to get rid of the k. So in order to factor it by the variance, which is the sigma squared, we have to let k equal to 1 over sigma squared, which is the same thing as 1 over the variance squared. Not the variance squared, it's just the variance. So we would get y is equal to 1 over sigma square root 2 pi e negative 1 over sigma square times 2 times x minus mu square. Since we have the square and the square, we can put this in one fraction, and the square root will cancel out. So now the whole equation is going to equal to y being equal to 1 over sigma times the square root of 2 pi, which is actually in another video of mine, the infinity factorial, which is very, very interesting. The infinity factorial is equal to the square root of 2 pi. So you can see that video. Times e to the negative 1/2 times x minus mu divided by sigma square. So this is the whole entire equation. And I can tell you the components of this. So since you know some elementary function knowledge, the e function is the exponential function, but since I negate it, I have the other side of the e function, and since I squared the x, I have a continuous function which looks like this. First of all, now the mu is going to move my function left and right. If mu is positive, I'm going to move to the left side. If mu is negative, I'm going to move it to the right side. So the mu is moving this left and right. The 1/2 is a factor, so it's going to squish it by like this, or it can widen it up. And also the sigma square is going to do this for me. And the factor in front is also doing the squishing and the widening of the e function. Now, since everything is on the denominator, I cannot make the function blow up to infinity unless sigma times the square root of 2 pi is less than 1. When it's less than 1, then sigma should be less than 1 over 2 pi at the square root of 2 pi, which is a very, very small number. But this almost never pops up, so this is a valid equation. Thank you guys for watching this very, very long video, almost 30 minutes. I'm very glad you looked until the end of the video. And I think this is a very surprising and also very mesmerizing solution, since we have two main constants of the universe, pi and e, playing in a role of many, many processes. So I hope you understood everything what I said. Like the video, comment on your video, my video, subscribe to my channel, and we will see us in the next video on Daishinfinity. See ya.